Today we are discussing on heat exchangers. The topic that we're discussing on is on heat exchangers. Heat exchanger may be defined as an equipment which transfers the energy from a hot fluid to cold fluid with maximum rate and minimum investment and minimum running cost. That means an heat exchanger is a device where the transfer of heat takes place from a hot fluid to the cold fluid. The best example for an heat exchanger is the radiator of an automobile. As all of you know, what happens in a radiator? The water which gets heated in the engine is supplied to the radiator tubes. On the outer surface of the radiator tubes, the fins were provided, and over these fins, the atmospheric air is made to flow. And this atmospheric air, while moving over the fins, absorbs the heat from the hot fluid. Thus, the exchange of heat takes place between the hot fluid and the cold atmospheric air by a combination of conduction and convection. And the water, by releasing heat into the atmospheric air, cools down and then it returns back to the engine. Radiator is one of the heat exchanger where the transfer of heat takes place between hot fluid to cold fluid, and it is a best example of heat exchanger. There are different types of heat exchanger and their classification is made on different bases, on different categories. The first category on which the heat exchanger is classified is according to the nature of exchange of heat between the hot fluid and the cold fluid. Based on the nature of heat exchange, they are classified into direct contact heat exchanger and indirect contact heat exchanger. Direct contact heat exchanger is also called open heat exchanger, and indirect contact heat exchanger is also called closed contact heat exchanger. And direct contact heat exchanger is one in which the exchange of heat takes place between the hot fluid and the cold fluid by direct mixing of the hot and cold fluid, and the transfer of heat and the mass between the hot and cold fluid takes place simultaneously. The best example for a direct contact heat exchanger is a cooling tower. A cooling tower is an heat exchanger in which the hot water coming out of the condenser cools down. The water which coming out of the condenser is supplied to the cooling towers. Is supplied to the cooling towers, and it is sprayed in the form of small droplets using nozzles. And these small droplets comes in contact with the atmospheric air, and a small portion of the water releases heat to the atmospheric air. Releasing heat to the atmospheric air gets evaporated, and remaining quantity of water cools down and falls through the cooling tower. Thus, condensation or cooling of the hot water takes place. Here there is a direct contact between the water and the atmospheric air. Therefore, cooling towers is a best example for direct contact heat exchanger. An indirect contact heat exchanger is one where there is no direct contact between the hot water and the cold fluid, or hot fluid and cold fluid. Radiator is a best example for indirect contact heat exchanger. As we know, there is no direct contact between the atmospheric air and the fluid or the hot water which is flowing through the tubes. The atmospheric air flows over the tubes and the water flows inside the tubes. Thus there is no direct contact. This type of heat exchangers are called indirect contact heat exchanger. The next classification of heat exchangers is based on the direction of flow of fluids. If both cold and hot fluids are flowing in the same direction, that type of heat exchangers are called parallel flow heat exchangers. You can see in the diagram, both the hot fluid and the cold fluid are flowing in the same direction in case of parallel flow heat exchangers. Since they are flowing in the same direction, the temperature difference between the hot fluid and the cold fluid is decreasing in the direction of heat transfer. But in case of counterflow heat exchanger is one in which both the hot fluid and the cold fluid flows in different directions. Since they flow in different directions, the temperature difference between the hot fluid and the cold fluid remains constant throughout the length of the heat exchanger. Therefore, the effectiveness of or the efficiency of counterflow heat exchanger is more compared to the parallel flow heat exchanger. The third one is cross flow heat exchanger. A cross flow heat exchanger is one in which both the hot fluid and the cold fluid flows at right angles to each other. For example, if the hot fluid flows from top to bottom, then the cold fluid flows from left to right at right angles to each other. The next classification is depending on the physical state of the fluids. Condenser and evaporators, they are classified depending on the physical state of the fluid. The heat exchangers are classified into the condensers and evaporator. As you know, condenser is a device where the condensation of the fluid takes place. Condensation is nothing but the change of state from vapor to liquid. And as we know, when a fluid undergoes change of state, the change of state takes place at constant temperature, either by releasing heat or absorbing latent heat. A condenser, the liquid, a steam, by releasing its latent heat to the cold fluid, condenses into liquid. Here the temperature of the hot fluid remains constant because it is condensing from steam into the water, whereas the temperature of the cold fluid is increasing because it is absorbing the heat from the condensing hot fluid. An evaporator is a device. At the same time, evaporators works in an opposite direction. In this case, the temperature of the cold fluid remains constant, whereas the temperature of the hot fluid is decreasing at a constant rate because it is releasing heat to the cold fluid, which is getting evaporated. Okay, next. The next concept is logarithmic mean temperature difference. The heat exchangers can be designed based on two parameters, by two methods actually, either LMTD method or effectiveness or NTU method. The first method that we are going to discuss is logarithmic mean temperature or LMTD method. Then what is LMTD? LMTD is defined as the temperature which, if constant, would give the same rate of heat transfer as actually occurs under variable conditions of temperature difference. Already we studied parallel flow and counterflow heat exchanger. What happens here is the temperature difference between the two fluids, that means hot fluid and the cold fluid, continuously varies. As the temperature difference varies, the heat transfer between the hot fluid and the cold fluid also varies. and it is difficult to measure temperature at every point of heat exchanger. Therefore, we are going to consider a constant temperature called logarithmic mean temperature, which gives the same amount of heat transfer which is equal to the actual conditions. That is called logarithmic mean temperature difference. It is the temperature difference at which if remains constant would give the same rate of heat transfer as actually occurs under variable conditions of temperature difference. It is for the sake of just simplicity of design. It is the temperature difference which if remains constant would give the same rate of heat transfer. And now let's go for the design of heat exchangers. In design of heat exchangers, as I already said earlier, the heat exchangers can be designed based on two types. Means there are two methods by which the heat exchangers can be designed. One is Lmpd method, one more is effectiveness method or NTU method. First, here we are discussing on the Lmpd method. Lmpd method for parallel flow heat exchange. Here we are discussing on parallel flow heat exchanger. Before we go for the design of heat exchanger, we need to make some assumptions. Before we go for derivation, we need to make some assumptions. The first assumption is the overall heat transfer coefficient U is constant. We already discussed what is meant by overall heat transfer coefficient U. When the transfer of heat takes place by combination of convection and radiation and conduction, instead of using conduction coefficient and convection coefficient, we will make use of a common coefficient called overall heat transfer coefficient. And this overall heat transfer coefficient is assumed to be constant throughout the length of the heat exchanger or throughout the process of heat transfer. This is the first assumption that we are going to make. Okay. The second assumption is the specific heat of both the hot fluid and the cold fluid remains constant. The specific heat of and mass flow rates of both the fluids remains constant. As we know, already studied, the specific heat of any substance varies with the temperature. Here also, as the hot fluid releases heat and the cold fluid absorbs heat, the temperature of hot and cold fluid continuously varies due to the heat transfer between the two fluids. Here what we are going to assume is, although the temperature varies, the specific heats of both the fluids remains constant. This is the second assumptions that we are going to make. The third assumptions are the flow conditions are steady. What is meant and steady state condition? That means the temperature, mass flow rates and other conditions remain same at a particular point with respect to time. Means the flow conditions are steady state. We are going to assume the steady state conditions. That means at a particular point the temperature of the fluid doesn't varies with respect to time, mass flow rate doesn't varies with respect to time. Means all the flow conditions with respect to time at a particular point remains constant, and there is no loss of heat transfer to the surroundings. That means we assume that the transfer of heat takes place only between the hot fluid and cold fluid. There is no heat loss to the surroundings. These are the assumptions that we are going to make in the design of heat exchanger using Lmpd method. Okay, now let us start the derivation of Lmpd, that means for parallel flow heat exchanger. Is design of heat exchanger based on logarithmic mean temperature difference for a parallel flow heat exchanger. First, instead of considering the entire heat exchanger, let us consider a small elementary area dA of the heat exchanger. dA, we considered a small elementary area. We will not consider the entire length of the heat exchanger. First of all, we considered a small length of an heat exchanger which is dA, having an area dA, small elementary area. We considered a small length of an heat exchanger which is having an elementary area dA. The rate of heat transfer through this elementary area, the rate of heat transfer through this elementary area can be given by dq equals U into dA Th minus Tc, where Th is the temperature of the hot fluid at that elementary area and Tc is the temperature of the cold fluid in that elementary area. Delta T is the temperature difference between the hot and cold fluid, that is Th minus Tc. dq equals U into dA into Th minus Tc gives the amount of heat transfer that is taking place between the hot fluid and the cold fluid in that small elementary area. Okay, we considered a small elementary area dA of the heat exchanger and the amount of heat which is taking place, which is the amount of heat transfer which is taking place between the hot fluid and the cold fluid through that elementary area is given by the equation dq equals U into dA into Th minus Tc, where Th is the temperature of the hot fluid in that elementary area and Tc is the temperature of the cold fluid in that elementary area. Okay, this amount of heat transfer which takes place through the elementary area dA is equal to the amount of heat which is transferred between the hot fluid and the cold fluid. dq equals minus mh into cph into dth means gives this equation, mh into cph into dth gives the amount of heat which is released by the hot fluid. We used negative sign here because the hot fluid is releasing the heat, it is losing its heat content, which is the amount of heat which is released by the hot fluid. The same quantity of heat is observed by the cold fluid, and it is given by the equation Nc into Cpc into dTc, the heat transfer equation at constant pressure. You studied all these equations in your BTD itself, and these two equations are equal to the U into dA into Th minus Tc, because this equation also gives the amount of heat which is transferring, which is exchanging between the hot and cold fluid. Okay, now we are replacing mh into cph by a term called ch and mc into cpc by a term called cc, c suffix c, where c suffix h it gives the heat capacity of the hot fluid and c suffix c gives the heat capacity of the cold fluid. Okay, now from the above equations we can write dTc equals dq by c suffix c and dTh equals minus dq by ch. We can write in that form. Now we can write dTh minus dTc equals dq minus dq into 1 by ch plus 1 by c suffix c. I have taken minus dq outside. On the right hand side I have taken minus dq outside. When minus dq is taken outside, we will left with 1 by ch. dth minus dtc, we get minus dq by dcc. If minus dq is taken outside, then we will get plus 1 by cc. Okay, but dq equals, from the equation number 1, we can replace dq with u into dA into th minus tc. Okay, where th minus tc is the temperature difference of between the hot fluid and the cold fluid of the in the elementary area, which is equal to theta. From the figure you can see th minus tc is the temperature difference between the hot fluid and the cold fluid, which is flowing through that elementary area, given by the term theta. Next, the equation reduces to the form d theta by theta equals minus u into dA into 1 by ch plus 1 by cc. Now integrating the terms, we know that the integration of 1 by x is ln x. Between the limits 1 and 2, we will get ln theta 2 by theta 1. Ln x, integration of 1 by theta is ln theta. We are integrating between the terms 1 and 2, we will get ln theta 2 by theta 1 equals minus the integration of dx is x, integration of dA is a, minus u into a into 1 by ch plus 1 by cc. Till now we considered a small elementary area. If we consider the total heat transfer between the two fluids, then the heat transfer between the two fluids can be given by the equation Q is equal to Ch into Th1 minus Th2, which gives the amount of heat which is released by the hot fluid in the heat exchanger, and Cc into Tc2 minus Tc1, the maximum outlet temperature minus inlet temperature. The maximum temperature minus inlet temperature is gives Cc into Tc2 minus Tc1 gives the heat which is observed by the cold fluid. From the equation number 5, we can write 1 by Ch equals Th1 minus Th2 by Q, and 1 by Cc equals Tc2 minus Tc1 by 2. Substituting these two equations 6 and 7 in the equation number 4, we will get ln theta 2 by theta 1 equals minus ua into Th1 minus Th2 by Q plus Tc2 minus Tc1 by Q. Taking Q outside, we will get ln theta 2 by theta 1 equals u into a by Q into Th2 minus Tc2. I rearranged the equations here. Th2 minus Tc2 minus Th1. I have taken this negative side inside and I rearranged this equation Th2 into Th2 minus Tc2 minus Th1 minus Tc1, and then rearranging the equations, we will get Q equals ua into Th2 minus Tc2 minus Th1 minus Tc1 divided by ln theta 2 by ln theta 1, where Th2 minus Tc2 is equals to theta 2, the temperature difference at the in outlet of the heat exchangers, and theta 1 equals Th1 minus Tc1, the temperature difference at the inlet of the heat exchanger. Q is equals to ua into theta 1 minus theta 2 divided by ln theta 1 by theta 2 gives the heat transfer through an parallel flow heat exchanger, for Lmpd method.